Okay. So are you able to hear me clearly? Yeah, I wonder if it is through the. Wait, let me just test my audio. Just now. Um, check. Anyways, so, so you don't have any. You don't get any background noise. Okay, it's as usual because here when I'm checking, the output is coming from the laptop and not through my earphone. But when you are speaking, I'm hearing it through my headphone only. Right. So let me just. Hmm. So let's start. If you have any questions, we can start with that. Or okay, okay, right, okay, okay. Um, y goes to 0. Right. So would you like to say how? Uh, yeah. Hmm. 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 Right. D. Okay. T. So, hmm. Okay. Can you make this more symmetric? If I just maybe you just write minus m. No. Yes. Yeah, that also works. Yes, exactly. That's what I. Right. Um, yeah. Yes. Mhm. Right. Mhm. Yes, right. Yes, I see. Yes, so this is fine. This is fine. Zero sequence. Hmm. 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 Okay, so right. Um, yes, that's a better, safer. Yeah, that will be needed. That is fine. Yes, I don't think I can say anything more in this. This is. Hmm. Okay, okay. Yeah, but this looks fine to me. However, you could think about if you like you could think about so you could think about the collection of all sequences which go to zero. Okay, you can try to look at that. So you look at C0 and you look at all. So instead of looking at one sequence, it's just you can look at the corresponding family yn such that, and you can call this C0. So now you can now try to see if you can um, you can define a notion of convergence for these sequences itself. Means how to say. So just a minute. You have these sequences C0. Yes. So you can define a notion of distance in this set. Okay. So you can exactly, yeah. So define a metric. So define a metric, and that this is going to be the soup metric. Okay, so you will be having something like x minus y equal to suprema this x and y and n. Okay, so then try to see that this becomes a metric space with this, and also it's a complete metric space. That's the key. So it will become complete. So if you take Cauchy sequences in this metric, so the elements will be sequences. This will be a complete metric space. Okay, so that is one thing. This will be a complete metric space. And if you now look at this CB, which is just bounded sequences. And yeah, if you look at this collection of bounded sequences, do the same thing. It will also be a complete metric space. See, yes, you put the same metric, and you can put the same metric because it's a bounded, so the supremum will make sense. So it's good to put that metric, and it will also be complete. And the C0 will be a closed subset of this. Okay. So what you will get is so what I'm getting at is just this, that you will have this C0 contained in this. Now coming to your problem, you can put a multiplication. You can put coordinate-wise multiplication operation and addition operation. So then these will become algebras, okay? Rings if you like. Okay? So these are rings, and that C0 is a subring. But then what you have shown is that C0 is an ideal. Okay, that's what you have. Yeah. Uh, yes. So when you quotient, you get the hyperreals. Yes, exactly. So do you take CB, or did they take something different? Hmm. Right. So you take all sequences, right? Not just bounded. You have to take all. Okay. Yes, yes. That might be the case. So hyperreals. Yes, yeah. So you quotient. So yeah, if you go there, if you quotient, then you will get the hyper. But before you quotient, you need to be able to say that these are ideals and so on, right? So this exercise is towards that, without the language of ideals. Okay. And maybe you would also like to show that it's a maximal ideal, so that when you quotient, you get a field, so that you can divide hyperreals and so on. Yeah. So now you can try to execute it. So then ultra filters, right? Yes, yes. So I mean, basically, um, yes, ultra filters would correspond to maximal ideals, or at least they would correspond to ideals in certain way. Yes, ultra filters would be basically some collection of subsets of natural numbers, and given those collection of subsets, you can pick certain sequences corresponding to those subsets and indices, and yeah, so in that way you get some idea. That would probably be an equivalent way to construct hyperlinks. Sure. Anyways, so that's an interesting thing, and basically there was a paper once I read. So basically the name of the paper was analysis is algebra or something like that, by someone called Hatcher, and they had done this. Not Alan Hatcher, exactly, not Alan Hatcher. Some yeah, William S. Hatcher, or William Hatcher at least. I don't know. Okay, so then let's move to the next. So so maybe YouTube suggested you that video because you tried this problem. I don't know. These things are very strange, and I don't like it personally. I get very uh-huh. Yeah. Yes, yes, and it's quite strange. I don't. It's probably not strange anymore, especially to you younger. I don't know, generation. I don't like it. It's like that's a word, right? It's uncanny. So yesterday also was talking with my professor about something, and suddenly in the evening it showed up. I decided to not open YouTube. It's very bad. I don't like it. I mean, it's like some might should some. Yeah. Anyways, yeah, let's. Yes, yes. So we should. Right. Mhm. Mhm. Oh. Mhm. Yes. Right. Yes. Yes. So on one side we can push the limit. That's a point. Yes, and because this thing tends to no, but this is infinity. Can you push the limit? I mean, you can, but do you need some more explanation? Let's think. They said assume the limit exists. Yeah. So let's see if we can prove that the limit exists. Right. Right. Means it is true, right? I think we can feel that the limit exists. So let's just prove it because it's otherwise there is nothing to do. Mm-hmm. Okay. All right, let's do that. So maybe as exposed to 0 from the right. This is also fine, I think. And here we can, hmm, okay, f of 1 over n. But then this one goes to 1, right? What is it going on? Okay, wow. Oh, right. Okay. So then it grows without bound. Right? So this one you are saying is infinite? Yes. But you see, so the argument you've given, it doesn't show that the limit exists because you have taken one sequence and how do you... Anyways, let's see the third part, then we can prove all this. Okay, so let's find that. P plus 1 over x. Like this? No. Oh, but it doesn't satisfy f of 1 is 5. Maybe hmm. Yes. Hmm. You can check that. P plus 2 by x by x plus 1. Right. But it's 5 plus, yeah, it works. So then it's done, right? This is the function. This is the function. This is the example. But yeah, so let's just prove this that x goes to 0, infinity. F of 1 by. Well, let's see. Yeah, you can. Okay. Oh, right, you're right. So then how do you conclude? Yeah, so then how do you conclude that? So you can conclude because it was given to be continuous, right? Yeah, so then it's done. Right? If you use that. You have to use that. Yeah, yes, that the limit exists. So just write it. So this exists by continuity, and hence your argument is sufficient. Yeah, so we have to come, yeah, do this. So this is fine, and but yeah, otherwise you are right. It's if it's not given to be continuous. Well, if it's not given to be continuous, then right, you can't do the first part, but okay, we do the second part if continuity is not. It is still possible, maybe. So continuity is not given, as you said that only about 1 by n, you can say. But still, so yeah, so if xn is a sequence that goes to 0, we cannot say about what is the limit of this. No, wait. If xn goes to 0 from the right, then what can you say about this? Well, this also goes to 0, right? So we just say xn is less than epsilon, so xn is, yeah, xn is between epsilon and minus epsilon. So then this thing is, let's say epsilon is less than half, then we have this 1 plus xn is bigger than half, right? And so we have, yes, it goes to 0, right? And it goes to 0 from the right, right? Yeah. So then, hmm, yes. Yes, f is not defined. We don't need that. We just need the limit, right? So to calculate the limit at a point, you don't need the function to be defined at that point. Yeah, we know that. And this is true. This is true because these are the points where in the exam, we can get a bit impatient, but still the reasoning might be important because the other things are easier. Okay. So our thing is to see if we can prove that the limit exists. Okay, if you can prove that the limit is infinite, or at least just prove that the limit exists. Right? If continuity is not, yes. So I've taken an arbitrary sequence then we get another sequence that goes to 0. That's the bad thing, I think. That might mean that uh, so, yeah, so if you can show that f of xn is unbounded for every n, for every sequence xn going to 0, does that show that the limit is infinite? That's a question. So that is true, right? Think about it. So if f of so if so this is certain relaxation when you are taking limits at infinity. So if f of xn doesn't have to go anywhere, but if it is unbounded for all xn going to, in this case, 0, so does this imply that the limit exists and is equal to, of course, infinity? Only the unboundedness, right? Makes sense, right? So let's try to prove it. So yes, if it's unbounded for everything, then uh, no, so I want to show that the limit as x goes to infinity is infinite, right? So, so just we have to just use the definition. So, if we want to show that f of xm is bigger than n, so for every sequence going to 0, yes, I'm just asking if this is true. So if f of xn is unbounded for every xn going to 0, does that imply that the limit is infinite? So you're saying that it should imply, right? I'm also thinking it should imply. So let us prove that. Yeah, so let us prove that. So suppose you take an m. I mean, it is almost just from the definition, right? But, so if you take an m, okay, and you want to find an x such that for all x prime, you want to find an x naught such that for all x bigger than x naught, right? F of x is bigger than n, correct? Right? So, right. And if this, now you see, if this doesn't happen, then you basically get a sequence, right? If this doesn't happen, then you get a sequence, right? You get that, okay, there is an x1 such that if not, so if not, then you get like x1, f of x1 is less than n, and x1 is bigger than x0. And similarly, you keep getting a sequence, right? Which is bounded from above. But that's a contradiction. So wait, so it's bounded from above, but we need to yeah. So it maybe I just write unbounded above. If it's unbounded above, then the limit of fx should be So we prove this. This is easy, and this is basically like when you say the unbounded from above, it what you see if you try to look at this, what this means basically is that if you treat this unbounded from above as an infinity, then it's basically meaning saying that for every sequence xn going to 0, there is a subsequence of f of xn which converges to infinity. Right, and then if you see that if you replace this infinity with an arbitrary point, then this is something which you know, right? And for every sequence, if there is a subsequence which converges to that point, then basically every sequence converges. F of that's what we are using. So it's slightly subtle, but it's true. It's simple. So right. So can we do that? Can we try to do that here? So let's just see for a few minutes and then we can, I think, it's later because these things can be interesting. What can be so yes, yeah. So if now you see if f of xn is bounded, let's say that if it is bounded, let's say from above and below. So I'm just writing bounded. Yeah. Then I can basically assume that it converges because there will be a subsequence. So this converges to some t, right? Some finite t. And this means that this other thing also converges, right? This other thing will also converge, right? Exactly. But it will also converge, and yeah, this is where we need the so that you see it. So we will need the limit to exist because otherwise we can't use. So if this converges to t and the limit exists, then I can say that this one also converges to the same limit because the input converges to 0. Then I can say that it converges to t also. Sorry. And then we get t equal to t plus 2 and we get that t is infinity or minus. I get a contradiction. But here, yeah, but I'm using that the limit exists. And if you use that, then you can just use your way. Probably easy. You're just taking one sequence. Okay. So there are two ways. That's my point. But yeah, without the limit existing, it's difficult. And I don't make the limit will exist. And that is something which I will try later. Yeah, it feels like it will not without the assumption. But we never know functional equations because if the solutions are very restricted, then it's true, right? Uh, so, uh, so that's fine. Let's continue. And similarly, sorry. So similarly, you should argue that this one also that the limit does exist because even though they have asked you to assume that, but you see for a continuous function, the limit as x going to infinity may not exist. Okay, the limit as x goes to infinity need not exist, right? Even if it's continuous. So you need to see. Um, However, oh, there is a problem. I'm sorry, huh? So even the limit at as x goes to zero need not exist. So maybe in the question they just assume that. Then it is fine. Yes, yes. But you see, conceptually speaking, the limit did not exist, even if you have continuity, because it's not a point in the domain. So, and you obviously have counter examples. Just take sine 1 by x. As x goes to zero, the limit does not exist. So yeah, so you have to be given that. But then again, that suggests that maybe from this equation you can prove it. I don't know. So that is okay. So these subtle things are important, especially because you're going to write the subjective or whatever. So, but anyways, you see, I mean, you'll have a lot of time. Don't panic about that. But whatever you write, it should be conceptually very clear. Okay, because obviously probably the tricky the trick bits and the things which you can do, I suppose, it's not going to be a problem, and it's never going to happen that the questions are going to be very tricky. You might have prepared more and more, but that won't make the question paper tricky. Okay, but it will depend on how well you write and you have explained everything. So even if there is a certain kind of argument which you don't like to give because you feel that they're true and you can prove it when needed, but in the paper, make sure to write everything. Yeah. So balance it. Yeah. That even if it's something which is a bit okay, there is maybe some induction or something, but you should do because you will never know it. It might actually not work if you try to write. So then you have to change. Yes. I don't know actually, but I would say you should do at least five. Yeah. But again, don't like even if it's not going like it's not going according to the plan and you don't think it's going to be five, then you should not panic about that. Okay. But you should make sure that you are writing everything honestly. Okay. Just you understand, right? Like if you can feel that your argument is not correct, and think about it and try to correct. Okay, and that's a habit which one can develop, right? Like for example, this limit question. So you see, like whether does the limit exist, does the limit not exist? It is needed, of course. Even the question, this question, they said that assume the limit is, they don't have to think about it. But the point is that when you're solving a problem, the problem may be inviting to you, but sometimes some of the details may not be inviting. You may not like them. Okay, but then it becomes a duty to give all the details as required. Okay. So that is thing which you have to remember, and don't give extra details which are not required in something. Don't need to give that, even if it's like that's your favorite kind of things to say. Okay, but that is fine. But you understand. So yeah, like if this kind of thing could happen where, like in integration, if there's some limit or something involved there, then does the integral exist? If it is required in the question to explain that, explain that. If it's not required, then you can skip. So yes, that's all. Otherwise, in the other parts, I think it's more straightforward. I mean, this rigor part is more straightforward. The problems can still be tricky. And like in polynomials in algebra, if you're using, then whatever theorem about polynomials you are using, it may be obvious to you and of course obvious to the examiner. So, but you should think of yourself as in class 12, okay, and then you should write all the details. Like if you say the polynomial has this degree n, then you cannot have n roots, and maybe you write that. And if you be careful if it's monic, not monic. Means point is you should know that there will be some simple way, and you have to just think. You don't have to complicate it more than me. Yeah. Obviously, most times we don't know how much we have to complicate, and that's why we end up thinking about all kinds of things. But anyways, okay. Yes. Yes. Inputs. Yeah. Right. Right. Hmm. Right. Sure. Yes, that's right. That's fine. Yeah. But it will just be like, I don't know, ceiling of n by 2 or something. Yes, 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 exactly. So it has to be that, but yeah, so how many weeks can you pick? And so the books are distinct or hmm, right. Hmm. Okay. You're picking three and right, right. Yes, yes. Right, right, right. Hmm. Hmm. Right. Yes, yes. Right, right. Hmm. Right. Hmm. Right, right. Hmm. Okay. Minus one. It's plus one. right, and and then we know the solutions for this plus k, right? Choose r minus 1. Wait. What was the formula? And then, yeah, ah, right, right. So it is this, and then we get n minus k plus 1. Choose k, right? Yeah. So then, what is the condition we get for k? Yes. So, yes. So k must be, yeah. So the same as the ceiling, because why? Because k is less than or equal to 1 plus 1 by 2, and so right. So does this mean that k is less than the ceiling of n by 2? Yes. So yeah, so the ceiling is rounding up to the thing, and if I do n plus 1 by 2, no, all right. So we know this, that it is less than or equal to the floor. Yes, because it's an integer, and then you want to say that this thing is equal to the ceiling. Not sure if this is true, but at least we should have this, right? So if n is even, then it is obviously true, and if n is odd, then so if n is odd, uh, then this will become m, right? And this will be also be m, right? And this one, the floor, this will also be m, right? So, but then are these two always equal? Wow. Why would we have a separate definition? But maybe it's because we check everything. So if n is even, um, hmm. Oh, they're always equal. Good. Then there's, and yeah, it's true. But I was just checking. Uh, right. Yes, so you can, I mean, you can obviously prove that the ceiling can be. Hmm. 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 Right. Not considering the book related chemistry. Right. So you have K plus that many books, which is also K. No. Or is it K minus one? Right. K minus one. And right. And this is more than the ceiling. So it's more than equal to ceiling plus one minus one. Yeah, and this is more than two. Yes, so it is just that. So, yes, but I mean in the exam also it will be just this. But yeah, one has to just efficiently think and write. Without the counting, yes, yes, because a lot of times the formula will not be there for a lot of problems, and then you have to do this kind of things where you have to space. So you know that there is a you have a claim, and then you can use that space. Like every point may require a radius of something. So how many things you can place. This kind of argument is it be used in many cases. Right. So this is so then it's good. I mean, it's fine to practice practicing. Yeah, and maybe do harder questions if you. Yeah, no need to do very hard questions, but so let's maybe stop for today. Just start from next time on time.